Today I'm going to start aberration. So let me tell you clearly that aberration cannot be covered in one presentation. So one presentation or one video, I want to break it into I think four or five presentations. So just hold on me. This is part one definitely, and I'm going to talk about aberration as an introduction first. Then today I'm just covering chromatic aberration. Then after part two, I'll try to cover few of the monochromatic aberration, and one of the central important topic in part two is paraxial approximation. What is paraxial approximation? Then we will go to all the five monochromatic aberration, which is basically Seidl's aberration, and the clinical correlations. Yes, and in one topic I'll try to cover small last topic is a Zernike polynomial, which is very important. Is current day aberration and how we'll examine Zernike polynomial in all the cases of. Let's take example of keratoconus and all the corneal cases and refractive surgery. So we will cover up slowly and slowly. Okay. So aberration. What do you mean by aberration? The aberration is a defect of image formed on optical system or defect of image forming property of optical element. Actually, aberration word came from the Latin word aberrare, which means to stray or to wander away the pathway. Aberrations means, see, it's simple. If this is point object and it is optical system, okay, it's a whole optical system. It is optical system, and this is point image. If point object forms exact same point image without the degradation, it is called perfect system, but it will never ever happen in reality. So there will be degradation of image as compared to object. So that degradation is no matter what called aberration. No matter what comes from diffraction, it comes from, I don't know, it comes from defocus and everything. Everything lies on aberration. So there is no perfect optical system. It is not invented yet. Okay. So we always try to decrease the aberration. If it is keratoconus, then we will put scleral lens. All the things. Okay. So to reduce the aberration, but it's not like that. You become aberration becomes zero, complete zero. It's not possible. So there will always be small defect in the optical system. It is impossible to create perfect ideal optical system. Okay, so can you see in this picture, uh, this is the picture of a strong chromatic aberration and this is the picture of corrected chromatic aberration. Isn't it difference? Is there? Yeah. So in every real optical system there exists deviation from the ideal that results in not perfectly blurred image. This imperfection is called optical aberration. So in every optical system it is there. In the area where we would ideally expect the formation of focal point, we instead have spot or the focus blur disk, and those is small called circle of least confusion. We think that its focus is perfect, but if we zoom it, then we can see there is circle of least confusion, not exact a focal point. It's always there. Okay, we will later on we will talk about it because in case of paraxial approximation, how it happens. Okay, so today I'm just telling you that we feel like it's the focus point, but if you zoom in, you can see that it's not a focus point, not exactly point, but there is also an element of circle of least confusion, which is definitely we have been discussing in some subconid. So, what is circle of least confusion? It is the extent related to severity of aberration in optical system. See, extent related to severity of aberration. It corresponds to the smallest transverse cross section at image plane, isn't it? In the image plane, circle of least confusion is a smallest transverse cross section point. So that's why we always wanted to uh, put our circle of least confusion at retina. That's why we have a term of spherical equivalent, isn't it? Sphere plus cylinder divided by 2, because it is the position of circle of least confusion, and circle of least confusion is smallest transverse cross section place at the image plane. So according to geometrical, it should be an ideal point because there is no ideal point, but what should be the appropriate and best point? So that should be uh, circle of least confusion. Even in the total absence of aberration, the wave nature of light sets the limit on how small the point can be. So I have already told you, if a total absence of aberration, so will be defect because of wave nature of light. So it's impossible to create ideal imaging system. Okay. So, the attempt to minimize or compensate the aberrations are evaluated by their effect on the size of circle of least confusion. Because size of the circle of least confusion is smaller, then focus is greater. Circle of least confusion is size is greater than defocused. It is the design of the optical system is not trivial task, definitely. Even perfectly designed system contains residual optical aberration because it is impossible to completely eliminate. I have already told you it is impossible to complete. The aim of the optical design is so-called corrected optical system, that is best possible reduction. So what we are trying to do when we design the optical system, we always try to do to reduce the aberration best possible. Okay, best possible. So lens designer takes into the account of following: the radius of curvature and various refractive error. We know that the surface separation and influence lens thickness and location, definitely. The material property, important refractive index, which varies in the material and wavelength, and later is called dispersion because the refractive index and dispersion is directly correlated. Size and the location of aperture stop, we have discussed about aperture stop, isn't it, along the optical system, because aperture stops gives the meaning to exactly exit people and entrance people. It depends upon the aperture stop. So these all things consider for uh, reducing aberrations, definitely. So when we come to the aberration, it's refractive index, dependence on wavelength, surface geometry, radius of curvature, wave nature of the light, and definite chromatic aberration, spherical aberration, other monochromatic aberration, eridix. This is called diffraction, isn't it? So these all points should be covered. So we have to understand like this. Okay. Today we are going to talk about chromatic aberration. So chromatic aberration. See, I want to make clear that chromatic aberration is an aberration of refraction. It's not an aberration of reflection. In mirror, there is no chromatic aberration because in mirror, angle of incidence equals to angle of reflection. So in mirror there is no property like dispersion of light. It will not disperse light because angle of incidence equals angle of reflection. So there is no dispersion. So chromatic aberration is a property of refraction. Okay, it's clear. Yes. So chromatic aberration is due to the material have different refractive indices for different wavelength, isn't it? What I'm calling, because in case of reflection there is angle of incidence equal to angle of reflection. So no uh, refraction, no dispersion. But here is dispersion because of different refractive indices for different wavelength of light, for different color, different refractive indexes. So longer wavelength corresponds to lower value of refractive index, and higher shorter wavelength corresponds to higher value of refractive index. So chromatic aberration, we discuss longitudinal chromatic aberration, another name is axial chromatic aberration, and another is transverse chromatic aberration or lateral chromatic aberration. Okay, two types of chromatic aberration. Whenever we talk about longitudinal chromatic aberration, it means we are talking about we are talking about, let me change this. If it is optical axis, then what we are talking about, red will focus on the posterior side of the optical axis and blue will focus on the anterior side of the optical axis, and this gap is called a longitudinal or axial chromatic aberration. Okay, so this is called longitudinal axial. The secondary focal length of the lens will differ for each monochromatic constitute. Obviously red is in posterior and blue or violet in anterior. It can be expressed as a dioptric difference between two extremes. So longitudinal chromatic aberration is omega ft, where ft is the dispersion power and v is a Abbe value. So this picture is, this formula is another very important. Longitudinal chromatic aberration is F, dispersive power divided by V, is a Abbe number. So we'll discuss about Abbe number later on in the presentation. In these two extreme cases, so this is Abbe value and this is dispersive power. Okay, so this Abbe number, which is another name, is contingence. The Abbe number, also known as contingent, named after the German physicist Ernst Karl Abbe, and it's the expression of medium of dispersion property. See, you pause the video and you can see, but can you say this formula? Refractive index is yellow light minus 1, and refractive index is blue light minus refractive index is red light. Almost that wavelength. See, it's very important to understand this formula, and that's why you understand the Abbe number of particular material. And remember one thing that's very important, note down this: Abbe number of human eye has value of 50.23, approximately 50 is the Abbe number of human eye. It's very important. Sometimes it's in MCQ, so it's just note down it. Okay, so Abbe number refractive index of various optical glass. Can you see this? This is here in y-axis. Index increases. In x-axis, what is this? Abbe value V. Abbe value is n, decreases. So can you see this graph? So it's like this. It's growing in upward direction. Slope is in positive. So higher the refractive index, the lower the Abbe value, which is very important to understand. Okay. So dispersive power is equal to Abbe value. Obviously, Abbe value is higher, the better, because more the Abbe value, the less the dispersive power. Okay, that's what I am telling about you. The longer wavelength focuses in the posterior part, shorter wavelength focuses in the anterior part, because shorter wavelength have greater n than this, isn't it? That's longitudinal chromatic aberration, and longitudinal chromatic aberration is based on the optical axis and focuses on different area. This is the longitudinal aberration, this difference between two focus point. Okay, so see in this picture, this is very beautiful picture from Professor Dr. Josh Asimeli's book. See, in this picture, this is the dispersive element, this is lens, isn't it? Eyes are blue and tails are in red. So tails focus posteriorly, but here you can see eyes are not focused. In anterior picture, eyes are focused but tails are not focused, isn't it? That's the aberration. So some color focus in inferior, in front of, and some color focus posterior of the optical axis. So it's shown so beautifully. So chromatic aberration in human eye. See, in human eye there is chromatic aberration between 380 to 760, which is approximately 2.5 diopter, and in linearly, which is approximately 0.93 diopter. And researchers suggest that chromatic aberration may be the cue of accommodation. And this chromatic aberration, this is the longitudinal chromatic aberration, is basis for what? For basis for duochrome test. It's always asked in presentation. This longitudinal chromatic aberration is basis for duochrome test. This longitudinal chromatic aberration is the reason why our lensometer has green target, isn't it? This is the reason. Now let's talk about the transverse chromatic aberration. Transverse means the height. Transverse means the height, isn't it? So it is not about the position of the image. Blue comes here, red comes here. It's not. It's about the height of the image. If the same object is same, then image height is different. For example, the image height of the blue color is smaller than image height of the red color is uh, larger. See, in case of chromatic aberration, object is always one, but image has a different color, isn't it? Because there is a dispersive material which is lens. So lens disperses the white color to different color. In transverse chromatic aberration, it's about focusing anterior and posterior along the optical axis. In case of transverse chromatic aberration, object is one, but image is two or many, because image has different color, and different color image has different size. That's why that size, height means transverse chromatic aberration. Are you getting the concept? Yes, that's very important, because object is one and image is Definitely size has different image size. One is larger image size, another is shorter image size, and that's what we call transverse chromatic aberration. That's what this picture is trying to tell you. Just pause the video and see. If you are if you want to know what is the lateral chromatic aberration, this is the formula, which is very good formula. Let's see. This is prismatic effect. This is Abbe value. Let's take an example. If someone has a polycarbonate lens, which is Abbe value is 30, and he has very high power 10, and he says from the 2 centimeter, from 10 into 2 centimeter is equal to 20, isn't it? So 20 divided by 30, which is approximately what happens there, 0.66. So now this value is lateral chromatic aberration. So this is prismatic effect, as we know, which is simple formula, power into displacement, and divided by Abbe value. If this value is greater than 0.1, then optical system can create problem. So here we go. The Abbe value, the greater the Abbe value is better, isn't it? In case of sorry, CR39, it's almost, sorry. In case of CR39, it's in almost 60. So which is better? This is double than polycarbonate, so it's far better. Okay, that's what the same thing it's talking about. Is it is the basis of both of the thing, isn't it? Transverse chromatic aberration. And so in this picture, can you see this? The left image is significant transverse, right image has significant transverse. In the border, can you see that red is hue, but this is in image left is low. It's clear, isn't it? So that's how we perceive it as transverse. Transverse means height. Okay, so this in this presentation I use all the books. Okay, this is a good books to start, and there are a lot of things from this book, and obviously my favorite of all time, Professor Dr. George Asimaris. So that's it, and I'll definitely see you in the next video, which is paraxial, going to paraxial approximation and few of the Siddle separation. Okay, for now, bye.